All right, we were talking about projectiles, these things that fly through the air, usually in parabolic shapes. Sometimes we think about air resistance and sometimes we don't, and hopefully you will learn lots about them. Let's talk about the horizontal motion and the vertical motion of a projectile. Now we got this thing, and as it falls, it is a projectile because it's being acted on only by gravity. And if you look at this drawing over here, every second it's going to gain about 10 meters per second. So at 1 second, it's going 10 meters per second. At 2 seconds, almost 20. At 3 seconds, almost 30, etc., etc. It's just going straight down, as you've hopefully dealt with before. But what if I launch it horizontally? How does its horizontal velocity and its vertical velocity compare? Well, it turns out that the vertical velocity is the exact same as if you just dropped it straight down. And at 1 second, it's going downwards at 10 meters per second. At 2 seconds, it's going at 20. 3 seconds, 30. Now its horizontal velocity, although, that's the exact same the entire time, because the horizontal and the vertical components do not depend on each other. And so let's bring that on here. Those horizontal and vertical components are independent of each other. That kind of leads us to the situation, whereas if you had a bullet here that I was just going to drop, and another bullet that I'm going to fire out of a gun, which one would hit the ground at the same time? And the answer is, if there's no air resistance, they would hit the ground at the same time. Because even though this is fired incredibly fast horizontally, it falls at the same rate as the dropped bullet. Now, shape-wise, I do want you to know that this shape is still a parabola. It's just only one part of a parabola. Not too much to say about this one. It's just that projectiles are flying in the shape of parabolas. So if we're talking footballs, basketballs, baseballs, anything where the amount of spin that it has on it is not greatly affecting it, and there's not too much air resistance to speak of, it's going to be in a parabola for objects that are not going crazy fast through a lot of dense air. The truth of the matter is, though, there is air resistance, and so projectiles do not always go in a parabola because of that air resistance. And if something is fired in a parabola, you can say that it will not travel as far, and it will not travel as high. Now this picture is an extreme case of it, but it's not going as far or as high because the energy is going to be lost to air resistance. And this might seem frustrating because it's harder to predict where things are going to land, but it makes curveballs curve, it makes footballers be able to bend kicks, and allows lots of exciting things to happen to an otherwise boring parabolic projectile trajectory. Doesn't get any more fun than throwing water balloons off the top of your school. And if your teacher doesn't let you do that, that's probably because he doesn't like you. You're not studying hard enough. Here at ISM, we do that. So will you try and solve this problem for this projectile motion? It only has horizontal motion to start with. First step is going to draw a picture. So pause it and do that now. You're often asked how to find the speed of something as it lands on impact. Well, first of all, let's back up and talk about how amazing this picture is. Here's our school. There's palm trees that have blue leaves due to the tropic I don't know why they're blue. But here's the half parabola that's coming off here. We want to find out how fast it's going on impact. You can actually not use any equations of motion, and it's easier to use the conservation of energy for this. So take a minute, pause it if you haven't done that yet, and use conservation of energy. You should be able to start with this and then end up with an answer. Boom! I just did it at the speed of light because I'm so fast. But keep in mind that the masses cancel out. That's one beautiful thing about conservation of energy with projectiles. And another beautiful thing is that direction makes no difference whatsoever. And that makes your life much easier. Hopefully this worked out for you. Now, pause it and work on part B to find out how far horizontally it lands. And as a hint, remember to separate your vertical stuff from your horizontal stuff. A common problem-solving method that works for projectile motion is if you're looking to find horizontal stuff, it's best to find the time first, or how long it takes for it to hit the ground. So to do that, you usually look at only the vertical stuff. And remember, always separate your vertical from your horizontal. And so if we want to find that vertical stuff, or find the time, pick an equation of motion that will work for you. And remember that the v initial in the y direction, I'm going to call this my initial y velocity, is 0 because it's fired horizontally. Here is the work for that. Notice what worked out nicely was that because I had 0 vertical velocity, this first term went away and made finding time easy. So then I plugged in my height of 16 meters, and I ended up with about 1.79 seconds. Now, pause it and use this to find the horizontal distance that it travels. The horizontal stuff is easy because there's no acceleration. Woohoo! So all you need to do is make a very simple distance equation with constant velocity. That distance is equal to velocity times time. And so we know that our x velocity is 13 meters per second. We know our time is about 1.79 seconds. Seconds cancel, and we end up with an x distance of about 23 meters. That is it.